this is the last video for chapter 19, chemical thermodynamics, and in this video we're going to learn how to relate the three chemical thermodynamic terms to each other. So far we've learned about delta H, delta S, and delta G, and we've learned how to calculate each of them individually using data from Appendix C. So when you watch this video, it would be best if you have your textbook nearby, because you're going to need thermodynamic quantities from Appendix C if you have access to that book. So anyway, what we want to do is how can we relate each of those three terms to each other? So the formula we're going to use was developed by Gibbs. That's why we call this Gibbs free energy. But the formula is delta G equals delta H minus T delta S. And T is the temperature measured in kelvins. So we want to look at the signs of these things. So if we consider when delta H is negative, if we think of delta H being negative and the T minus, or the negative T delta S term being negative, then delta G will always have to be negative. And we learned before that if delta G is negative, it always means it will be a spontaneous reaction. Now we can look at the opposite of that, assuming delta H is positive and the negative T delta S term is positive. If that's the case, then delta G is always going to be positive and the reaction would not be spontaneous. We're going to have issues with predicting spontaneity of a reaction when the terms delta H and negative T delta S have opposite signs. So for example, if delta H and negative T delta S have different signs, then the sign of delta G just depends on how big those terms are. So if the positive is bigger than the negative, delta G would be positive. If the negative sign was bigger than the positive, obviously it would be negative. And that means that temperature then is the important factor there. So when we use these formulas, we want to make sure that we always have our temperature in kelvins. And if we're using the values from the back of the book, remember, the back of the book always has this little degree symbol by the values. And that little degree symbol stands for standard state. Standard state implies that you have 1 atmosphere of pressure and a temperature of 298 Kelvin. Now technically it's 298.15, but standard state conditions are very different than STP, and we've talked about that once before, but it doesn't hurt to remind you. So whenever I'm seeing this little degree symbol, you should always think of a temperature of 298 Kelvin. Now, the only way to really get into this is to just practice some problems. So we're going to do that here in just a moment. But we want to talk about this third bullet point for a moment. And a lot of times you will see this up on the IB exam. So you want to be able to kind of reason through what's going to happen. We've already talked about if delta H is negative and the term that negative T delta S is negative, then you're going to always have a negative sign. But it's when they're opposite that we have issues. So we're talking about here, if we have a delta H that's negative and a T delta S term that's positive, then it's negative at low temperatures, delta G is negative at low temperatures and positive at high temperatures. Now you don't have to copy this chart, it's on page 825 of your book, but it's good to look at. Now if you think about the example I'm giving you here, let's just look at this example. Liquid water turning into solid water, okay, so we call that process freezing. Now, water will freeze at low temperatures. Anything lower than 0 degrees Celsius or 273 Kelvin, that will be a spontaneous process. Water, if it's lower than 0, is going to freeze. But if the temperature is high, it's not. Okay, water won't, at a temperature above 0, water will not freeze. So we have to kind of keep in mind the temperature is a factor. And then you look at the bottom choice when delta H is positive, so it's endothermic, and the negative T delta S term is negative. If you think about that, then we have it being positive at low temperature and negative at a high temperature. So the opposite process, taking solid water, so ice, and melting it into liquid water. If we have a low temperature, ice is not going to melt, but if we have a high temperature, it will. So use this logic to kind of help you make some predictions. But if we look at how we actually do the problem, this should be written on your sheet for you. It says hydrogen chloride, which you guys know as HCl, and ammonia, NH3, escape from bottles of their solutions and react to form white glaze that you often see on glassware in chemistry labs. And the reaction is given as HCl plus NH3 makes NH4Cl. Now, the first thing it's asking you to do is calculate delta H for this reaction. Now, without any values given, you would want to use the values in Appendix C. Okay? And I don't remember if your book has this one, so I will give that to you. But you want to remember that delta H of any reaction is always equal to the sum of all the delta H's of the products minus the sum of all the delta H's of the reactants. So in this reaction, we're going to look up ammonium chloride's delta H value. And if it is in your textbook, hopefully it is, but I think I got this from a different book. It's negative 314.4 kilojoules per mole. And since the coefficient out here is a 1, I'll just multiply that by 1 mole. And then I'm going to subtract that from the sum of all the reactants. So HCl gas should be in your book, and so should NH3. And HCl is a negative 92.30 kilojoules per mole. Again, times 1 mole. And that is plus the NH3, which is negative 46.19 kilojoules per mole, and then times 1 mole. Now, make sure you do your math carefully. Remember, you're subtracting what is going to be a negative number. So your overall answer, when you do this, should be a negative 175.9 kilojoules. And the question says, is this reaction exothermic or endothermic? Now your delta H that you just calculated was negative. So hopefully you remember that that means that it is exothermic when your delta H is less than 0. Moving on to part B, calculate delta S for this reaction. Now remember that delta S is done very similarly to delta H. The delta S for the reaction is to take the sum of all the entropy values for the products and subtract that, or subtract the sum of all the S values of the reactants. So using Appendix C data, you should look up for ammonium chloride. It should be 94.6. Now remember with this, the label is joules per Kelvin mole, and we have 1 mole of it. And then subtract from that the values for HCl, which is positive 186.69 joules per mole Kelvin times 1 mole, and then add the other reactant to that, the NH3, and that is a 192.5 joules per mole Kelvin times 1 mole. And again, do your math carefully. Remember, you're adding together the reactants, and then it's products minus reactants, and you should get a value of negative 284.6, and the label would be joules per Kelvin. And so the question asks, is the entropy increased or decreased? Well, because the value is negative, the entropy is decreased, which means it's getting more ordered. And you should have been able to predict that sign just based off of the reaction. You have 2 gas molecules, so 2 molecules are forming 1. Just the number of molecules alone are becoming more ordered. And then you're going from 2 gases to 1 solid. Solids are definitely more ordered than gases. So hopefully you could have predicted that that should have been a negative number. Now, it says using delta G equals delta H minus T delta S, find delta G. So now, although you could do this using individual G values, we want to verify that this equation works. So delta G equals, now delta H we found to be negative 175.9 kilojoules. And then minus, and we want to plug in our temperature. Now, since we were using standard state values, the temperature here we want to use is 298, technically 298.15 Kelvin. And then we're going to multiply that by delta S. I just want to make sure you see, though, that delta S has a label of joules per Kelvin. All of my other measurements are in kilojoules. So I'm going to need to convert the joules to kilojoules. And to do that, I'm going to simply divide by 1,000. So this becomes negative 0.2846 kilojoules per Kelvin. And when you do your math, you should see that the Kelvin terms will drop out. And when you do this in your calculator, you should get a delta G value of negative 91.0 kilojoules. And so the question is asking us, is this reaction spontaneous or non-spontaneous? Well, when delta G is negative, the reaction is always spontaneous. Now you could go through and find delta G like we did the other two quantities by summing up the products and by subtracting the reactants, and you should get very close to the exact same answer. Now, the question says, the last part of this question says, at what temperature will this reaction be at equilibrium? Now, the question is, when is equilibrium going to occur? Well, we should remember that when delta G is equal to 0, the reaction is at equilibrium. So we're going to take our reaction, delta G equals delta H minus T delta S, and we're going to set delta G equal to 0. And we're going to use our delta H values and S values from the previous problems. So if we look back, delta H was negative 175.9 kilojoules. We're solving for the temperature. And the delta S value, remember, keep it in kilojoules, is a negative 0.2846 kilojoules per Kelvin. Now, to solve for the temperature, you could move this to be 175.9 kilojoules over to that side, and you're going to be left with negative T times negative 0.2846 kilojoules per Kelvin. And if we divide both sides by this negative value, you're going to get an answer of negative 618 Kelvin equals negative T. And so hopefully you can figure out quickly that T must have to be equal to 618 Kelvin. So this reaction will be at equilibrium when the temperature is 618 Kelvin. And that is how you use that formula. So we will practice more with this in class, but hopefully this covers the basics for you.